So, hello, Professor Graham.
I miss Pachakofe.
You are muted, actually.
Yeah, I think you are muted, Professor Graham.
Yeah, okay, so no, it's a great meeting. I think you're doing a perfect service, not only for the Indian community, but really for the rest of the world. And it's a fantastic meeting. Thanks for doing it.
Yeah, and thanks for all of you supporting it, because it's a really hard time we are going through, and it's still like the people's enthusiasm and so on is very encouraging for us, because it's a very young and new community, and it just things are starting. But students seems to be very excited.
So are students also coming on the weekend? So today is a Saturday. So does that matter at all, or?
Well, with the lockdown and everyone being at home, I think the sense of weekend has dissolved.
Has almost vanished, yeah.
Every day is a weekend in some ways.
Yes.
Yeah. Yeah, it must be very hard for students, particularly working from home and with different scenarios.
I can imagine, yeah. And so how is access to internet for everybody? Does that work halfway as well, or?
I think that's the only great thing about the timing of the lockdown, that in India, we really have a very good network now. There's 4G in most places. So the network connection has been really, really good. And that's how, for example, in IITs where we are actually running the whole entire semester, the course, everything, all exams, everything online. In fact, now the end semester exams are also going on. And even after that, like a lot of students are joining. And it has been working very well because of this very well-structured internet connections.
Yeah,
So,
for us,
otherwise, I cannot even imagine it would have been all a black hole, effectively.
I mean, for us, we were still suffering. I mean, many people, their upload connections were many times like at the edge of being sufficient. Yeah.
But now things are normal in the lab, like everything.
Yeah, more or less. Yeah. So we try for the individual teams to just stick among each other. Yeah, so that we don't mix like everybody. Yeah. And that seems to be working well.
And you have in-house testing.
And then we have testing, yes.
So the classes have resumed?
No, classes are all online. This is all online. There's no, there's only the lab courses. They are taking place in presence. Yeah. We also all with testing. Yeah.
Okay.
But all the lectures, they are online. So we are very much used to that kind of format, actually. Yeah.
Okay, that's great. Yeah, we are doing exactly identical things.
Yeah.
Okay,
but I guess it's the same for you.
Yeah. Yeah. So the two other organizers, Professor Bimalendu Dev and Professor Sourav, is also here. And Sourav, should I start? No.
Hi. Yeah, I think we can. Yeah, we can start it.
Okay, so let me just start by introducing Professor. It's a great pleasure to introduce Professor Selim Jochim, a professor at the Heidelberg University. And Professor Jochim actually did his undergraduate at University of Heidelberg and PhD at Innsbruck, Austria. But I think both under the supervision of Professor Rudy Graham, who is also here today in the audience. He spent a postdoctoral stint at the IBM Zurich Research Lab, should I call it an industry? And has been after that in Heidelberg ever since. And as a part of his PhD work, Professor Jochim actually in Professor Grimm's group demonstrated the first trapping of fermionic molecules and eventually demonstrated the first BEC with molecular lithium, exploiting the three-body collisions, a specialty of the Grimm group near Feshbach resonance, which transformed the way people thought of BECs prior to that. Currently, his work, current group works primarily on the strongly correlated fermions and the field of few to mesoscopic regimes. Particularly, I just wanted to make few comments that in many ways, Professor Jochim has been a pioneer of mesoscopic AMO physics. In particular, his group exploited what is otherwise impossible in condensed matter mesoscopic systems of building this Mesoscopic Systems atom by atom. So just one of his papers, which I felt had a quintessential title capturing his interests. This is a science paper, 2015 or 16. Which was titled that from few to many, observing the formation of a Fermi C1 atom at a time. And the first line of that abstract goes as knowing when a physical system has reached sufficient size for its macroscopic properties to be well described by many body theory is difficult. And I think that has been his primary goal of really teasing us, thinking of this thermodynamic limits. In recent years, of course, his group is just producing striking, mind-blowing results on Pauli crystals, Higgs modes, few particle precursors to phase transitions. And that's we hope to listen today. Professor Jochim also wants to start. I see there are enough number of participants. So he wants to start with few quizzes, being an exceptional teacher. And so if we all join, so actually we can use the reactions in the Zoom to say yes or no. Is that what the format you like to get the quiz answers graded? Okay, yeah. So over to Professor Jochim.
Yeah, thank you very much for the very nice introduction. Yes, it's a great pleasure to be here, and thank you very much to all of you for organizing this. So what I will be talking about today is understanding many-body physics from the correlations between the atoms, and building up quantum systems now atom by atom in order to understand the ever-growing complexity of these correlations. So what is the ingredient here really? For us, we had always, you have been hearing a lot about cold atoms these days, an ultra-cold Fermi gas or just any ultra-cold gas. So what is it characterized by? I just want to recap what you've already learned over all the weeks. We have extremely low density. So there's in between each particle, there is a separation of on the order of a micrometer or so. But yet, the range of the interactions between the particles, if they are not really strongly polar also have a strong magnetic moment, the range of the interactions is actually a nanometer. So that's 1,000 times less. So how come this can in any way be an interesting scenario? So just as Saikat also just mentioned right now is the question that I would like to ask you some questions, because this is like what every ultra-cold gas looks like, and I would like to see that you come along with this and how I should react on certain how you will give answers to this. So my first question for you is, why should it be so dilute? And just to have it simple, there will be just possible to answer yes or no to these questions. And the first question is, the diluteness helps us to prevent the system from recombining through three-body collisions. That's the first questions I'm having for you. Is this correct or is it false? And then you can just use, if you go to the participants list, there's a button that can say yes or a button that can say no. And if you just use that. Someone said something in the chat. Okay, that's also fine, You can also, so everybody says yes, so that's good. And I see no, so I'm happy about that. So indeed, that's true, That's how we make it so dilute, Because as it's dilute, the chances are two particles can meet, but chances are way lower that three particles can meet. And so three-body collisions, which are in many ways interesting, are quite strongly suppressed compared to two-body collisions. That's correct. So the next question that I'm having for you is, interactions can be treated as essentially point-like if the temperature is low enough. Is that correct? Considering that there's basically only this van der Waals interaction, which has a nanometer of range. Can I consider these interactions to be essentially point-like? You can also ask in the chat some questions if you would like to have some more specification on the question. So now I see no answers yet. So what do you think? Yeah. So the interactions between these particles, van der Waals, can I see this as point-like or not? What could be? So I see that. Do you need any more help to understand the question? Because there's also not many answers.
The divisions are not there. There are, I think, 4 yes, 2 no's.
Yeah, it's fine. It's fine. So that's why I'm asking the question. I mean, I want to know, what is too difficult and what is too easy. Yeah. Yeah. So that's exactly. So if I don't hear any answer,
count is 4 yes, 2 no's.
4 yes, 2 no's. Yeah. So this is so this question I need to explain a little bit. Yeah. So indeed, you can consider the interactions between particles as point-like, and to actually find the proper answer is to do scattering theory. Yeah. And you do a partial wave expansion, and you find that only so-called S-wave collisions, which don't include any angular momentum, play a role. This is that, and then you find the S-wave scattering length as the only term. But you can see a very simple argument why any structure of the scattering potential doesn't play a role. Woody says no, yes, because it's not always the case. You can debate, Woody, in just a moment. Yeah. So the simplest explanation I just want to give is if the wavelength of the wavelength of the waves scattering are much larger than the size of the objects that are scattering, then in principle they are not able to resolve the structure of the objects they scatter off. Yeah? So this is like in optics. If you have a microscope and you want to resolve something, the wavelength needs to be much smaller than the object you want to resolve, yeah? Or the same order of magnitude at least. Yeah? But if we go for very, very small momenta, then the wavelength of the particle is very, very long, and they're not able to resolve the individual potential. So now Woody can give a comment and say why this is not correct, what I'm saying.
You need
Okay.
to unmute.
So,
yeah.
I try to unmute. Okay, I'm unmuted now. I think it's in many cases the answer is yes, but not in all cases. Yeah.
Yes.
And it depends on, what happens if you have an effective range. So there's one problem of the resonance. Yeah. An effective range, and if you work with fermions, you always have a finite momentum, for example, so the effective range becomes important. It's not, then the answer would be no. Or what happens near resonances where, yeah. So it's not, I don't know whether, I'm not sure whether that is what you meant, yeah?
Actually, I can save myself by saying that, my argument was I want the wavelength to be large enough such that I can't resolve any structure. And that would, in this case, also apply to the effective range. Yeah, I still need to have momenta which are large enough to resolve
it's a limiting case, and
yes.
You have to define the limit exactly what you mean.
Exactly. Yeah. In the limit that the wavelength is much larger than the structure I want to resolve, I can't resolve it. Yeah?
That's true for a two-body, but if I have a Fermi sea around and I have a finite Fermi energy, then I have a finite momentum.
Okay, then I would include the Fermi momentum to the the wavelength will be shorter due to the Fermi momentum. No? I mean, I want to only look at the two-particle collision in that case. But it's good to have this kind of debate. Yeah. So you should never agree on something before you know what exactly we are talking about. Yeah. So that's I think that's the lesson we should take from that. Yeah. You should always debate. Yeah. Okay. Someone wants to ask a new question or? No, this was just
I
from
just
you.
made
Yeah,
a
you
line
wanted
for
just
if you are asking new questions too, so that you see the answers.
So, of course, and I mean, I didn't want to shove too much under the rug here, but for the talk that I'm giving today, indeed, it will be true. Yeah, the interactions can always be considered point-like. No, that is not true always, and especially if you look and if you design your experiment in such a way, and Rudy has exactly done that in many ways. That's why he immediately jumped in. Yeah, to design the experiment such that you can actually probe and look at the non-point likeness of the interactions. Yeah? Okay. So let me check what I wanted to say next. Yeah. So now the last part, if the interaction, my last question on this slide here, if the interactions are actually point-like, yeah. So how do they play a big role in the system, or is it other things like temperature, kinetic energy, thermal energy, Fermi energy that play the most important role to describe any physical system built out of these ultra-cold atoms? So that's the question, yeah. Can the interactions even play like a big role? Sounds a little bit difficult to answer, right? Someone says for Fermi systems, yes. Someone says interactions plays a crucial role. Okay, let's have a look. Okay, this I already said. So okay, I forgot that I had written this down on my slide here. Oops. The answer that I wanted to give to the point likeness. Yeah, and of course you can replace this by van der Waals, by for other length scale. Yeah. This is just a very general argument, yeah, which you might design things that it doesn't hold. But now the tunability, yeah, of interactions allow us to make the interactions very strong, even if they are point-like, and that's very interesting, yeah. So that's the regime we are always working in, yeah. We use magnetic field Feshbach resonances. That's actually something that really had a big rise when I was a PhD student with Rudi Grimm. So that's where I learned to use all of that. Yeah. So there's the one number that characterizes S-wave scattering lengths. This point-like scattering. That's the S-wave scattering. Yeah. At low temperatures. Yeah. So I'm simplifying again. Yeah? And you can simply tune a magnetic field, and you can make this scattering length infinite. Yeah, you can make it very large and infinite, and when it's infinite, it turns sign, becomes negative. Yeah, so that's the interesting part. And what comes with it is, if you have a very large positive scattering length, there's even a molecule being formed, and it has a definite binding energy, and that binding energy is just given by this formula h bar square over ma square, and that energy is actually precise, but you could also deduce this just from dimensional arguments, yeah? And has huge wave function, even though the interactions are only point-like. That's what's called a halo molecule. Huh? And so this is not only the system when it's bound, yeah. So we can now have a molecule that we can tune in size. We can make it huge. We can make it much bigger than the interparticle spacing. Okay. Then there's also another way. We can also put a repulsive interactions. Yeah, that's again positive scattering length, but we don't use the bound state. And I just want to show this to you as a very simple example that everyone can do the calculations for themselves. Yeah, you can maybe later go on and have a look at this. Just take two interacting particles, and we put them in harmonic trap, and we use only one dimension. Okay, we use only one dimension. And then we can write down the Hamiltonian, and we can solve everything ourselves. Yeah? So that's written down here. We have the momentum of the first particle, momentum of the second particle, the potential the first particle sees, potential second particle sees. And then we put in an interaction term, and in this case, it's really just a delta potential, delta function, because I said the interactions are point-like. Huh? And then there's a prefactor which tells us how strong the interactions are. That's it. It's very simple. And every one of you can solve this. Just take into account that the interactions are, of course, only in the difference coordinate. And if you see this, then it makes a lot of sense to do a separate, to separate the center of mass motion from the relative motion. Just what you do when you do the solve the hydrogen atom. Yeah. So you define some coordinate x2 minus x1, and another one which is x2 plus x1. And the relative motion is, of course, only in this coordinate, and you can separate the Hamiltonian according to both. And you find just one Hamiltonian, like one particle Hamiltonian here, center of mass, momentum, relative momentum, the potential term, and then the interaction term as the delta function. Yeah? Okay, that's very nice. That's really just everywhere beside the point x equal to 0, that's the harmonic oscillator. And you can solve that piecewise. Yeah? You know how to do this, for example, for the box potential. You always do in quantum mechanics course, you do a piecewise solution of the Schrödinger equation, the exact same thing you can do here. Yeah? And you can already notice, if for any antisymmetric solution, like this one here, this Hamiltonian will already be will also have exactly that solution, yeah. No matter how big the interactions are, yeah, because there's a 0 where this Hamiltonian has some non-zero value. Yeah? And then for all the symmetric solutions, there will be just introduced a kink, a non-continuity, which is allowed due to this delta function. Okay. And so what will be the solutions? Yeah? At 0 interactions, you will just get the harmonic oscillator solution that you know. And then I said, you get some kink exactly here at this point. Yeah. And if you make that the repulsion between particles stronger and stronger, the strongest repulsion you can make at infinite repulsion, if I make this term infinite, then I have to constrain the density to 0 at x equal to 0, and I get this kind of solution. And interestingly, it looks very, very similar to the solution of the first excited state of the non-interacting system. That's why this is called the fermionized solution, because it looks exactly the same as the wave function you would have for two indistinguishable fermions, which have to have an antisymmetric relative wave function, a 0 at the, but the symmetry is of course the same as that of this. These are relative wave functions, by the way, between two particles. Huh? So if you want to read more about this, a very nice paper to read for all of you is this paper by Thomas Ghosh from 1998. This treats this not only for like the one-dimensional case, but 2 dimensions and 3 dimensions. And it's very instructive also to understand or get intuition for interactions between more than 2 particles, okay, in such a system. But what you can see here already, just from what I showed you, is that the interactions, even though they're point-like, they can be just as strong as the other energies in the system, okay, if you tune this situation right. Yeah, and there was actually a very nice experiment that was done by one of my students, Gerhard Zürn, to exactly observe this kind of situation. Yeah, and we called this the fermionization of fermions, because it was 2 fermions that actually were distinguishable fermions that were made to have a wave function that looks like that of indistinguishable fermions. Okay, so by the way, if you have any questions, just also write them in the chat. I put now the chat window on such a place in the screen that I can actually also see it, so that you can immediately react to it. Also, just unmute your microphone and ask aloud if you want to ask a question. I'm happy to immediately answer. Yeah. So okay, so that is this. Yeah. So interactions are important. Yeah. That's what I wanted to explain with this. And now, what are we really after? We are after understanding how like many bodies physics works. Yeah, and there's very simple cases if I take moderately weakly attractive situations, then many of you might have heard in condensed matter physics, there's one important scenario that's called the BCS type of superconductivity, where very weak attraction leads to the formation of Cooper pairs. So that basically at the Fermi surface, if this is the momentum space here, I can take this as a momentum picture here, then the BCS theory tells me that if I have one particle at the Fermi surface, that would be the Fermi surface here, the largest momenta that the system can have, there will be one other particle with opposite momentum. Okay, and so that means if I look at the Fermi surface, I will find an opposite momentum there, and that is cute and interesting and very helpful. But that is already has been understood for a long time. Yeah? So that is a situation when the scattering length is smaller than the interparticle spacing. Okay. But what's even much more interesting is if that is no longer the case. If the scattering length is very large, that is, for example, if these molecules that I showed you in the beginning, they will be much larger, each of them, than the spacing between the molecules, then these molecules would have to overlap, and you can already see that makes it complicated to understand. Yeah. So that has and the extreme case that the scattering is infinite, that's called the unitary Fermi gas, and that has been always a big challenge to somehow even like a very conceptually simple system to understand it. Huh? And like a lot of people, Rudi, myself, many others tried very hard to really get more and more understanding of it. Yeah. But so for a long time, from all the experiments that we took, it was somehow clear that it's important to understand. Now, we can't just say, aha, at the Fermi surface, there will be pairs forming there, but there's actually much more complicated correlations between all the atoms, and we would like to understand all the correlations between all the atoms. And that was somehow a driving scheme between all the experiments that my group has done during the last years. Yeah? So this is somehow related also then to these quantum gas microscopes, but we want a little bit more. We don't only want to actually detect correlations in real space, but we want to also detect them in different spaces, yeah? In a more general way. Yeah? Okay. So, and then, so there's a big question mark then, how do you want to actually go and reach this many-body limit in such a way that you can control and understand each and every correlation that the system has, yeah? And for us, this was always thinking, aha, if I build like a few-body system one by one, then what do I have to do to actually reach a behavior that's typically annotated with many-body physics, like phase transitions. Every one of you knows what that is. If ice melts and becomes water, or it evaporates, then that's a phase transition. And of course, for this, you need like a macroscopic system that this actually works. You know? So how do we obtain this collective behavior? And so there's, of course, atoms, nuclei, and so on. They're all in this regime. But I should say there's quite interesting pioneering work by Tönnies and his group a long time ago, where they put little molecules as probe into helium droplets to see how they turn at which kind of numbers they turn to become a superfluid. That these molecules actually probe a superfluid. You know? So that is actually also something interesting to read. This Physics Today article here, that is very readable, you know, for you if you're interested to dive into this question more. Yeah. Okay. Then now, how do we address? So that's now an experimental thing. Yeah. How do we address the question to really build like now these ultra-cold atom systems, atom by atom? Because usually we are talking about a gas. Yeah. And the systems I will present you later on, they're actually, I mean, you don't need to think of them as a gas. They're actually like a well-defined quantum system. Yeah. Well, the basic idea is very simple. If you have a Fermi gas, yeah, then the Fermi gas is described by some Fermi surface. And at the Fermi surface, you have some excitations. You have holes inside the Fermi sphere, and you have some excitations outside, some particles which sit outside. Yeah? But inside, every state is occupied by exactly one particle. Yeah? That's what a Fermi gas is characterized by. And now the major idea behind everything that we do is that in principle, anyway, we do evaporative cooling. We remove in a deterministic way the particles that have a kinetic energy that is higher than the threshold of the trap. But why not then go and in a controlled way lower the trap potential such that we really cut very deeply into this Fermi sea to have like basically no excitations remaining. Yeah, so that's really the basic idea, and that has been working now for many years, and I won't explain you in so many details how we do that. The idea is the following: you need a potential that's already filled, like with atoms, and it's a degenerate gas that's at the lowest energy levels are occupied by more or less one particle of each spin state that you want to consider. And now what we do is, because as you see here, any potential at the edge will have many states as the potential becomes very flat. What we do is we tilt that potential to make that edge a little bit sharper in such a way that most of the quantum states that the potential supports are unbound, and there's a fixed number of bound states remaining. Yeah? And then only these bound states that are remaining should be filled with an atom. Yeah? So the actual challenge in the end is to make sure the tunneling rate through this barrier that you create here is actually small enough that the lifetime of the state is large. Yeah? That gives us a fidelity for most experiments larger than 90% to prepare like systems that now have like that are actually now very fixed in all degrees of freedom. Yeah, they have no choice to somehow adjust because there's actually a Fermi sea where every state is actually filled by one atom. So all the correlations are already fixed between all the atoms in this way. Yeah, that's very nice to start out with. Yeah, it's a very controlled system. Yeah. So now the other experimental tool that I will be using is that we can detect individual particles one by one. Yeah. And you've probably seen already, yes, you have already seen experiments with quantum gas microscopes where atoms are imaged in optical lattices where they are frozen to not move around. Now, what is the case for us? We would like to image the atoms in somehow in free space at arbitrary positions. And our approach is actually a very simple one in this respect. The idea is we would like to just collect fluorescence that we shine on the atoms while the atoms move around, but we collect enough fluorescence from each atom that we can determine its position well enough before it has moved and diffused too much. And that's a little bit challenging because as soon as the atoms start to scatter photons, they will move around a lot. Yeah. Yeah, but in our system, we can collect about 25 photons or so from one atom on average before they have moved too much. And it looks a little bit like this. So that's first now a background image of what we see from what we see in a certain field of view of our camera. We use a very sensitive, single photon sensitive camera. And that will be an atom. Yeah, you can very clearly see there's now a cluster of photons appearing on the camera, and that's an atom, another atom. Yeah, another atom. And you can see now here there's many pictures of the same area, and there's just very few ones where there was no atom detected. Yeah, so that's how it works. We can now detect individual atoms. Yeah, so that works with some very high numerical aperture lens that we can also use to shine light on the atoms to create potentials. Yeah, we can use what's called a spatial light modulator to adjust the size of these so-called tweezers that we apply. Yeah, to have a waves between like 1 and 5 microns. We can do several tweezers with an acousto-optical deflector to make, for example, double wells, and I will show you some examples of that. And there's one other aspect. We use some laser beams from the side, which come in here and interfere and produce a lattice in the vertical direction. And we make sure the atoms are trapped exactly in one layer of this lattice, such that we effectively have a two-dimensional lattice in this direction. We have actually little pancake-shaped traps that we can look at with this microscope above. Okay, so that's what the experiment looks like. You've probably seen many pictures during the last days. And I will just go and show you some of the experiments because I already lost half of my time. I want to show you now something. Yeah? So there's 3 things that I would like to show you. I will first show you some experiments on correlations between atoms that we prepared in fixed positions, yeah, in the 2 double valve positions. So that's the most simple thing you can actually do. The second one is look at correlations between atoms when they're delocalized in a trap. That's a little bit the situation I explained to you for the 2 particles in the harmonic potential, but they're now already 3, and they're indistinguishable in this case. So for both these cases here, we won't use any interactions, just to make life very simple. And the last part, I will take you, I will show you some results where we actually use the same system that we use here, delocalized atoms, but we introduce interactions, and I will show you that we can actually see something that's very much like Cooper pairs for a small system. Yeah? So let's start with this first thing here. This is very much related to the Hanbury-Brown and Twist effect. You can, for example, read about like what this has been like studied with photons in this reference here. So what do we do? What is very nice with our atoms, we can prepare 1 atom each in 2 separate tweezers, and that's basically separate preparation of 2 individual atoms. In some sense, these 2 atoms, they can't see each other. Yeah, they can't know of each other. Yeah, we just prepare 2 individual atoms in 2 tweezers. Yeah? And now you could say, aha, they have nothing to do with each other. So how? So what should be their correlations, or what should be any correlation between them? Yeah? And what we would like now to find out, what is how are they correlated in momentum space? Yeah. And for this purpose, what we do is, I mean, if you want to know about momentum space, one very simple thing that you can do is you can just switch off all the potentials, then the particles fly apart, and you do what's called time of flight imaging. Yeah. And what we do in our case, because we need to keep the atoms in the plane in which we image them, we actually don't let them fly in time of flight in free space, but we actually let them fly in some waveguide that goes along the connection between the 2 tweezers. Yeah, because we are interested in the momentum correlations along the axis of the connection between the 2. Yeah, so we switch off these 2 tweezers, and then the atoms can move freely in the direction connecting the 2 tweezers. Yeah, that's what we do. Okay, so that's and then we take an image, and you can see the image of the 2 atoms here, and the position of the 2 atoms encodes now the momentum of each of the 2 particles. And of course, so for this experiment, we use 2 times the same spin, so that 2 particles are indistinguishable. We don't know which one is which. Yeah, which one came from which tweezer. That's important. Yeah, and then what we can do is we can record the momentum of the first particle and the momentum of the second particle. Yeah, so that gives us a 2-dimensional diagram. So it's only the 1-dimensional momentum of each particle gives us 1 point here. Huh? And if we do this experiment many times for many implementation, we get a result that looks like that. Yeah. So what does that tell us? It tells us, first of all, we can have a look at the diagonal here first. Yeah. It means the 2 particles cannot have the same momentum, even though they started out from 2 different tweezers. Yeah, we didn't tell them which moment both atoms don't know which momentum the other atom has. Yeah, so that is prevented. Yeah, because they have too large a distance from each other. Yeah, but still they decide for themselves that they can't have the same momentum. Yeah, that's because they're indistinguishable. Yeah, and you can see, of course, then further fringes. They look very much like the fringes from a double slit, but notice. Fringes from a double slit. If we were to place 1 atom in such a double valve potential, then each of the 2 atoms would have some of these kind of interference fringes, and they would go along 1 axis here. But if I integrate out 1 particle here, if I were to record only the position, the momentum of 1 particle, that would just have some kind of close to Gaussian distribution here. Yeah? So this is a purely an effect that comes from the indistinguishability of the two particles, and that gives this shows us that the particles have correlations, even though they don't see each other, they don't know each other, just because they're indistinguishable. So now there was the question: are these single shot images? I don't know if I saw that on time. What do you mean? These images here, or?
I think the earlier the single photon, those photon pictures that you were showing.
This, sorry, I didn't see it. So
Yeah.
Each of them is a single shot. Yeah, and these are the individual photons that are recorded on the camera. On one picture here, one frame, it's just many photons, but one atom, one shot.
So these are EMCCD, like.
This is an EMCCD that records single photons. Yes.
Okay, great. Please go ahead.
That's how it works. Yeah. Actually, I can tell you, if you use rubidium, I didn't even tell you what kind of atom we are using. We are always using lithium, yeah, and lithium is very lightweight. It's lithium-6 because that is the fermion. And if you were to do this with rubidium also, it would be so much easier. You probably wouldn't need an EMCCD camera. It could be much easier done. Yeah. Just if any one of you wants to try that. Yeah. With most atoms, that should be much easier than with lithium. Yeah? So that is that. Yeah. But now I'm going to have to go back. Yeah, so this is really from the contrast. Now you can tell what the interference, how indistinguishable actually the particles are. Yeah? And we actually know what limits our contrast. It's kind of interesting because we let the atoms expand in this waveguide. The waveguide is not perfectly aligned with the axis between the two bells, and so that means that the way how they are released into this waveguide is a little bit affected by from which tweezer the atom comes, yeah, and it gives us there's some slight possibility to get a cue from which tweezer the atom actually came, and that limits the indistinguishability and the contrast here. Yeah. Okay, so that is now just two individual fermions that interfere even though they don't know each other. Okay. And in principle, we now do the same experiment. And the only thing that we do differently, we don't put them in separate potentials, but we actually put the fermions now in one potential, one harmonic potential. And to make that kind of interesting, we actually put the particles in a two-dimensional geometry. So now we are using the interplay between this lattice in the vertical direction and the tunability in size of this tweezer that we use, and we make this tweezer a little bit larger such that the track becomes oblate. Okay, and now we do this spilling experiment that I showed you in the beginning to control the particle number. And the interesting part is now, as we lower the trap depth, we get some plateaus here. Yeah, one here is 12, one is 6, one is 2, and by now we can actually, I should have updated this graph, we can also do 20. Yeah, we have another plateau here. Yeah, and these are the plateaus that just come from the fact that now in this two-dimensional harmonic oscillator, there are the generate energy levels. Yeah, so the ground state is only one level. The first excited state is actually twofold degenerate, the third threefold, fourfold, and so on. Yeah, and while we lower the trap depth, we somehow constrict the particle number to kind of filled shells. So we call this the degenerate energy level shells. Yeah, just like in an atom. And the interesting part is the number of atoms in the shell goes very slowly compared to, for example, in atomic physics. Yeah. Okay, so we can prepare these systems quite nicely. Okay, these numbers are also a little bit outdated. We can do this better by now, but it's similar to that. Yeah. So we can prepare now filled shells. And now if we want to do, so what we can't do yet very well is we don't have sufficient spatial resolution yet to image the atoms in situ. But for many things, it doesn't matter so much. You can just also go and measure their momenta. In particular, in a harmonic oscillator, the eigenstates of the harmonic oscillator in real space are exactly the same as those in momentum space. Yeah? That's kind of interesting, an interesting effect of a harmonic oscillator. And so the idea is we do a time of flight of these particles and then measure their positions. Yeah, so that's what you can see here. Yeah? And interestingly, the particles, interestingly, you can see in many pictures, that's a single shot again. Yeah, you can see somehow some structure. It looks like there's one atom at the center. There's 5 atoms around. Yeah, and now if you take many of these shots, then you see it's not always quite like that. Yeah, so it looks sometimes also more or less random, but sometimes you still see this structure. So now, how do we reveal that there's actually really some structure, some correlations between the atoms? And there was actually some neat trick it's my daughter, she wants to take part. So how to arrange the individual pictures such that you can actually illustrate the correlations present in the system. So the idea is the following, that first, what we can easily remove from our system is the center of mass motion. Yeah, we can simply, the center of mass is just a quantity that adds some extra blur to it, so remove that. Yeah, and the next thing that we can do is, that's this part one, our trap has perfect cylindrical, or close to perfect cylindrical symmetry, so there's no preferred rotation of any correlations between the particles. So it makes sense to rotate each image with respect to the other one such that their overlap is better. Yeah. So now there's one question. I maybe stop for a short moment and read the question. As you showed earlier, the photon from an atom can come in different direction, but when you are measuring the momentum using imaging, then how are you controlling the direction of photons coming from the atoms? So the photons are always going in 4 pi solid angle. Yeah, and we are collecting only a small fraction, about 10% of all the photons. Yeah, I don't know what exactly the question is. We are not measuring the momentum. So we are measuring the position of the atoms always. Yeah, and we are collecting a small fraction of the photons in our camera. I don't know if that's not the answer to your question, then just ask again. Yeah. So the true position of the atom is not the same as the atoms. The atoms are actually diffusing a little bit while they scatter photons, and that's the limitation of how big the spots are here. Yeah? The spots here, spot size here is given by not by the resolution of the optics, but indeed by the diffusion of the atoms while they fluoresce.
No, so
yeah, maybe that was.
Hi. So my question is, I mean, when you are measuring the atom position using imaging, so when you are getting photon and at some particular direction, then that is not the true position of the atom, right? Because as you are saying that you can collect the photon in the 4 pi solid angle.
Mm-hmm.
So when you are measuring the, I mean, corresponding position of the atom, so that position is not the true position, right? I mean, because you are measuring the photon, basically it's coming from the atom.
The photon coming from the atom, but I'm imaging the photons coming from the atoms using some optics, and so I take an image of the plane in which the atoms are trapped.
But you are taking single shot imaging, right? You are taking single shot image when you are.
But I'm always collecting many photons from one atom.
Okay. So you are averaging that. I mean,
I'm not averaging. I'm just collecting something like 25 photons from one atom.
Okay.
So okay, because I'm scattering. I'm collecting like 10% of all the photons. Yeah, we are collecting 10% of all the photons that are scattered because that's a solid angle of the objective.
That's right. Yeah. Right.
Or it's a little bit bigger. That's 14% or so. Yeah. But then we lose some photons also, and the detection efficiency is finite. Yeah.
So can you say the true position of the atom? I mean, that collecting the photon, can you identify the true position of the atom? Because
yes, why not?
because a photon can come in any direction, right?
Yeah, but it's an image. It's an image. So the image. Let me try if I can draw here. Oops. Why don't I get it now here? So your atom sits here.
Yeah.
Your lens is here. Your screen is here. So any photon, whichever angle it comes from, it will hit the screen at the same point, at the camera at the same point, right? Something like this.
Right.
I didn't draw it well.
Right.
Yeah.
Yeah. Okay.
Yeah.
Yeah, we can come back to this. I think.
Yeah.
That's an image. Yeah.
Right.
Okay. Okay, and then of course the only problem is I have to collect enough photons, because there will be also some background, and there's of course a fluctuation of the photon numbers that you detect, and that will give you some finite detection fidelity and so on. Yeah, but actually by now that works pretty well. Yeah, that's pretty accurate by now. Okay. So now I of course spoiled here my slide. Let me quickly. I can't find my pen. That's why I was a little bit struggling. Okay, it will be fine. I think you can still see it. Yeah. So now what we do is we rotate each of the. So we move the center of mass, and we rotate each image such that the overlap between all the images gets maximized. Yeah. And so what you see here is then the result, or an average over many images. Yeah. And then now you can very clearly see some structure which comes from the fact that the individual atoms kind of repel each other, even though there's no interaction. So that's, I should note here, there's zero interactions between all the particles that are present here. Yeah. Just remember, when I showed you the two particles in the harmonic trap, the antisymmetric solutions, they're always the same, independent of how strong any interaction potential is. Yeah, and that is reflected here. Yeah, so if the particles are all indistinguishable fermions, then there's only antisymmetric wave functions between two particles, so no interactions. Yeah, in this limit of point-like interactions, which Rudy of course disputes rightfully. Yeah, but in our case, that's correct. Or at least we can assume it to be correct for the scale we are looking at now. Yeah. Okay, so that's what it looks like. Yeah. So and really, the spatial order comes only from the exchange symmetry. There's zero interactions. Yeah, that's the kind of the interesting part here. And that is now here for the 6 atoms. It works the same for 10 atoms, or for 3 atoms after all. Yeah? Now, when you look at this little structure that you see here, you might always wonder, is this maybe just some artifact of how we do this analysis, how we do these rotations and so on? Yeah. And there's one very easy way of checking it. You can just heat up the system very slightly. Yeah. And we just shake it a little bit. Yeah. To heat it up. And what you can see here is then just a little bit of shaking, and so that the average energy is now increased by just around like 1 harmonic oscillator energy, and you can already see this correlation pattern that kind of was becoming visible is basically going away. Yeah. Yeah, which tells you, most probably there's it's not very easy then to come up with something that just comes from the analysis. Yeah? That in the imaging. Yeah? So you really see these beautiful structures arising from this, and they're called Pauli crystal after Marius Gaida, who kind of coined this term. Yeah, I would be a little bit. I'm sometimes not quite so happy with this name, although it sounds very beautiful, because it's not really a crystal after all. Yeah? This is some structure that appears, but actually also vanishes and gets weaker and weaker as the system grows bigger and bigger. It's also an effect of few particle physics, because we know Fermi gas, large-scale Fermi gas is isotropic. No? So this kind of structure will actually be washed out. If you go, you can already see that the n equals 6 cases has much less contrast than the n equals 3 case. But it's beautiful. I love it very much. Huh? So I'm very happy about this. Yeah, because what does it tell us? Yeah, it tells us a way how we can actually visualize correlations between particles, even though the correlations are actually not only 2-point correlations, but correlations between each and every particle in the system. And that's usually something that's very hard, and we still need ideas to find out how that actually works. Yeah? So now I have to rush a little bit because I want to still show you the last pictures. So that's the Pauli crystal. Now we introduce interactions, and a few things I have to tell you. Now when we are talking about energies, we also always need to see about which scale we are talking about. Yeah. So now we introduce interactions, and we have to compare this with 2 other scales. One is the energy in the trap. So that is basically given by the trap frequency, the spacing between individual trap harmonic oscillator levels. So that's one scale. And the third scale that you have to consider, that's the Fermi energy. That's basically how many of these levels are filled. Yeah. Currently, we fill only very few shells. So this Fermi energy is always somehow comparable to the trap frequency. Yeah. It's not very much larger. Yeah. Okay, so we get rid of this. And I would like to go a little bit fast here and just say now what we can very nicely prepare is these filled shells, yeah, where basically all the quantum states in one given energy shell here are filled, yeah, and that gives a very nice, interesting scenario. And I want to just go quickly over it. Because all the energy levels in one shell are filled, if you now introduce interactions, there is no way the quantum state can be altered by the interactions if you don't occupy also orbitals in the next higher shell, which costs you immediately this energy scale of 1 trap level. Okay, you have to invest this amount of energy, yeah, and that makes any pairing, yeah, that you need that requires the rearrangement of the wave functions quite highly suppressed, as long as the attraction is much weaker than this distance between the trap levels. Okay, and that gives an interesting behavior, because now you can only have pairs between the fermions if the attraction between 2 particles is strong enough to overcome the energy to the next trap level. Okay, and that gives something that is kind of interesting, because normally the superfluidity of fermions can happen at every attraction strength. Just the critical temperature will go to very low values if the attraction is weak. But here in this situation, there's actually a critical attraction above which superfluidity can occur. Yeah? And where this should show up is in this phase transition to a superfluid, from a normal to a superfluid, is in the excitation spectrum actually becoming gapless at the critical point. And this we could have a look at, and we could just go very briefly. I just jump over this, is too much detail here. While we tune the attraction strength, we can see the first excitation actually going down, having a minimum, and going up again for 6 atoms, 12 atoms systems. And this minimum would, for many body system, then actually end up to actually close the gap to 0. You know? But we can already see the effect of this kind of gap closing as the particle number increases. So that's one thing. But I would like to also show you now. So now for weak attraction, now we won't expect pairing, but for strong attraction, we should see pairing. And the question is, can we see this? Yeah. So now what we do is, so far I showed you images where there's only one spin state. Yeah. And because this was like just a polarized Fermi gas. Now we have 2 spins, one spin up state and one spin down state, and they can interact between each other. So what we take now is, again, these time of flight images, but we're interested in how are the different spins correlated? Can they form pairs? Okay? Can they form pairs? So we do this time of flight again, and we take an image. This is one spin state. We take another image, and that's the other spin state. And the small circle here, that should illustrate what is the Fermi momentum of the system. Okay? And we can superimpose them both to one image. Now you can see in different colors the two different spin states and their momenta. And the question is now, can we find correlations among them? So now these are many, many shots showing the same thing. And they look like kind of random, okay? But what should we have if we have, for example, this BCS type of correlations I told you about in the beginning? Then we should somehow find to each particle at the Fermi sphere, we should find a particle at the opposite side of the Fermi sphere. And okay, can we see that? Yeah, we need to do a little bit more analysis, and I can't now. I go a little bit fast over it, but the idea is the following: what we do for this is we fix one particle here, yeah, and then look where are all the other particles. Take the density of that, yeah. That's the kind of a second order correlation. We integrate them over 1 degree of freedom, you know, and subtract the density, and that's what it looks like. What these images then look like. We fix one particle at one position, and then look where are the other particles. Okay, and we can now move that particle around and bring it closer and closer to the Fermi sphere, and we see nothing. It's also not a big surprise because these were data taken at very small attraction between the particles. But now we can use the Feshbach resonance and tune the attraction between particles. And we do the same thing. Yeah, we fix one particle, or we take all images where one particle has been sitting at that point. Let's say like that. Yeah, and now we can move. We can just choose other images where one particle has been sitting further outside, and you can see, aha, now this density plot doesn't look homogeneous anymore. But indeed, as we choose particles sitting at the Fermi sphere, we find that there is an opposite spin particle at the opposite side of the Fermi sphere. Yeah. So that's kind of the most naive way of thinking. One could call this something like a Cooper pair. Okay, but I have to conclude. I'm already over time. Sorry about that. So, okay, this I won't show you now. And just okay, maybe also I don't show you this if you have some questions on this. So, but now really this is the most simple correlations that you could imagine to observe. What we already know that they are there, but for very strong interactions they should be different. Yeah, and this is what we would like to find out next. Yeah, really understand how exactly from these microscopic images understand what the correlations are in such systems. That's really our goal. Yeah. Okay, and with this I would like to thank you for your attention, and I would like, of course, to thank my team for all the great work they did for a long time. Yeah, it's actually their work, not mine. Yeah. Oh, thank you very much.
So thanks a lot, Jochim. So are there any questions? I don't see any questions in the chat. If anyone wants to ask, can just unmute. I think I had a question. I think I missed at the very end. So the Fermi C, you are basically just estimating and drawing the circle, or do you see anything special happening in Fermi C?
So this I mean, this circle that we draw, this is just really the calculated Fermi momentum for that particular system. Yeah, because I mean we need to have some reference where you know that's. And of course the other position that's of course we take all the particle all the images where an atom has been close to that point that we draw. Yeah, that's the idea. Yeah, this was maybe really too fast.
Do you see anything happening special at those momentums, or this correlation of upspin downspin? Is that special at the surface or Fermi surface, or
yeah, that's exactly what these images show. Yeah, I mean if you look at these images here, you can also see. Yeah, most of the time the momenta are within this Fermi, this circle. Yeah, and of course, this circle will only be sharp if you have many particles. Yeah, if you have few particles, the circle will never be sharp. Yeah, even at 0 temperature. Yeah? So that's why that's perfectly fine that you see particles outside this Fermi.
So these are how should I think of this? These are like kind of high excitations already because there are particles outside. Like
no. This is so really just fewer number of. This is just coming from the fact. I mean, you have a wave function, like many particle wave function, and you take a snapshot of that. Yeah, And of course, this wave function has some Gaussian tails. It has some distribution, and that's what's reflected in these images. Yeah?
So these are not like Landau-like excitations. These are just actually the ground state.
What do you mean by Landau-like excitations?
I'm saying like just
really
due
due to the fact that that you actually have interactions, then you have to have actually. Okay, so how much is the like what your question is basically, how much is the density already distorted by the fact that you have interactions? Yeah. That effect is like for the strength of interactions that we have here is still pretty weak. Yeah. The size, actually, we have another plot, but I don't have it in this graph, where we plot the average size of the cloud, yeah, as function of interaction, and that doesn't tune very much yet, yeah, because that's also interesting. You can then find something like, Woody might be interested in this, the Birch parameter for a very small system, something like that, yeah. Yeah, that's the kind of how much is the overall energy scaled with the interaction strength, yeah. That's still a weak attraction for that purpose, yeah. But indeed, yes, it might also play a role, and already I think, yeah, it might be interesting to look at what you asked for, yeah, in more detail. Yeah, we didn't analyze it carefully enough to see if we can, like, basically the single particle energy spread is different, yeah, maybe on a microscopic scale. Not really what we looked at is the overall energy, but it might be interesting to really look at the distribution more carefully, and then you might see what you're asking for. No, that's a single particle observable. We're already looking for the higher order thing, but this is actually also interesting indeed.
And just another quick question, that like when you actually turn off this little dipole traps to let this fermions interfere, do you have like kicks from the this turning off of the dipoles, like how adiabatically you're doing, and based on that the visibility depends on that?
So for this case, it's deliberately turned off instantaneously, yeah, because we want to, I mean, we want to capture the in situ momentum, right? Yeah, so so there's no adiabaticity, or there's no we try to do this as instantaneous as possible, but because it's with an this is an acousto-optic modulator that we switch off, it switches off within, I don't know, 150 nanoseconds or something like that, and that's much faster than any time scale of the system. Yeah, so that doesn't play any role. That's instantaneous for any purpose. Yeah, so it's really the instantaneous, the in situ momenta of the particles. Yeah. The only trouble that we might have is that we actually don't really do a real time of flight. They're not expanding in free space, but along one axis, because we couldn't do it otherwise. In this experiment, we had to make sure the atoms don't expand in the z direction, because then they go out of focus. Yeah? And then we didn't have another way to just have them only expand in the plane. Yeah, and for that reason, what we had was this tube, yeah, in which they expand, and with this tube was luckily aligned along the axis of these two tweezers, such that we can actually obtain the momentum distribution of the pairs. Yeah, the momentum correlation is in the interesting direction. Yeah, but because this was then again not perfectly aligned, you know, with the axis of the two tweezers, that gives us somehow the some finite contrast after all, yeah.
And last thing, your lenses are inside the vacuum or outside?
They're all outside the vacuum. And we're building a new system. We still put them outside, but we make the system the vacuum system much smaller, such that the lenses can be are easier to build. Yeah, because now this is a big steel chamber with some inverted viewports, and the distance, like the working distance of this objective, is very large. Yeah, and it makes it actually tough to build. It was actually designed by a former student of mine. Yeah, it was kind of a heroic thing. I would not do that anymore these days. Yeah, but I think the student learned a lot by this. Yeah, and it helped him a lot in his further career to have done this. Yeah? So he doesn't regret having done this, but it was a tough job. Yeah.
Okay, Professor Jochim, like, thanks a lot for your time and being here for this discussion meeting. And I guess like it's time for, unless you want to make any closing comments, it's time to move to the next talk.
No, just thank you for giving me the opportunity to be with you. Yeah, it was fun for me.
Thank you. Thank you. Thanks a lot.
Thank you very much.
Okay.
Thank you.
Then I will stop sharing my screen.
Sure. Yeah. And I would over to Professor Bimalendu Dev for the chairing the next two talks, the last two talks of the session.
Thank you, Saikat. So welcome to the second session of the day. So in this session, we have two speakers, Professor Yosuke Takasu and Tapan Misra. So I think Professor Takashi, can you hear me? Professor Takasu?
Yeah, yeah.
Okay,
Hello.
okay. Good to see you. Good to see you. So let me introduce our speaker, Professor Yosuke Takasu.
Yeah.
Professor Takasu is currently Associate Professor at the Department of Physics and Astronomy, Graduate School of Science, Kyoto University. He works in experimental ultracold atoms, in particular in the fields of degenerate quantum gases. Today, he will talk about quantum simulation using ultracold 2-electron atoms in optical lattice, non-equilibrium dynamics, and fermionic Hubbard model with SUN symmetry. So with this, I invite Professor Takasu to present your talk. Thank you.
Thank you very much for kind introduction. So my name is Yosuke Takasu from Kyoto University, Japan. So first of all, I deeply thank you for inviting me to this online workshops, and I am very glad to talk our recent experiment using ytterbium atoms. Okay, so here is my outline of my talks. So after quick introduction, so I will talk the two topics. First is about Hubbard model, so and the non-equilibrium dynamic as the third quench. And second one is a Fermi Hubbard model and the measurement of short range SNL magnitude. And then I summarize my talks. Okay. First, I would like to show our collaborators. So as all of the experiment was done in Kyoto University under the supervision of the Professor Takahashi. So and also this is another experiment members. But this experiment is very important to the collaborate with the theoretical team. So actually, so for the first topics of the non-equilibrium dynamics, so we collaborate with the Kindai University in Japan. For the SN spin correlation system, so we collaborate with the Rice University in the United States. Okay, so so now I talk about the so introduction of the quantum simulation. So yeah, so here we consider the many-body quantum systems. So, for example, the electron in the solid state is a very good examples. So, for in general, so many cases, the Hamiltonian itself is already known. But in that case, so this is written as Hubbard Hamiltonians. But in that case, so, but in general, so, but it for the this many-body quantum system is difficult to solve or to simulate using quantum computer, especially for the very large-scale systems. So and probably so many theoretical researcher is make an effort to some approximation to solve this so quantum many system. But in contrast, so we can prepare another so many-body quantum systems. Yeah, this sorry. Yeah. Sorry. Okay, so this Hamiltonian is the same for this many-body system and this many system, but this new system has a good controllability, such as cold atoms in the optical lattice system. So this is anyway. So we can this controllability means that we can change the parameter of Hamiltonian very easily. So the new system can be simulated. This new system can be simulated this system. So the Richard Feynman is initially developed this idea and is now called as the quantum simulations techniques. So especially in our work, so we use this myself, so quantum many-body systems use the cold atom gas as a benchmark of the computer simulations, as shown here. So now I quickly show the numerical method for the quantum many-body system. So in general, for the 1D systems, we can use a very powerful numerical calculation method such as the DMRG or method using the max product states. But in contrast, for the higher dimension and also for the large scale system, there is no good numerical method. So, but fortunately, so for in the case of the experimental viewpoint, so the experimental tool for the 1D and 2D or 3D systems is almost the same, almost common, and we can extend the experimental 1D to the 3D to very easy. So so now it is possible to do this. Sorry, I mentioned now. So first, we check the validity of this the quantum simulation or validity of our experimental results using this powerful numerical method of the 1D systems. And then, so we extended that to the higher dimensions cases. The experimental results would be a good benchmark for the numerical method. Okay, so now I talk about our the laser cooled atoms. So this is our periodic table. So the red one is atoms which are already successfully cooled by the laser cooling techniques. So in our lab, so we focus on these ytterbium atoms. So one of the advantages is that the ytterbium is a 2-electron systems. So there is a 2 electron of as a valence electron. So this means that there is a 2 metal superstate states, and also there is a 2 ultra narrow transition from the ground states and then to metal superstate states. So and then this the natural values of these transitions are less than 1 Hz. So and very good for, especially this transition singulated 0 to P0 is used as so-called optical lattice, optical frequency standards. Another advantage is that the ytterbium atoms is very heavy. So ytterbium has a very rich isotopes. So 5 bosons and the 2 fermions. This is very important for the quantum simulation because we can easily tune the parameter by changing isotopes. Okay. So actually, we already observed the boson condensation using the 4 bosonic isotopes, and also the 2 fermions gas is successfully obtained. So another one bosonic atoms, 172 ytterbium atom, it has a very large attractive scatter length, so it is impossible to create a stable species. So in this means that we already successfully all the quantum gas for all possible all isotopes. Okay. So now by using all these boson gases, we recently focus on the physics in the optical lattice system. So probably another lecturer already talk about this optical lattice system. But I will quickly explain the optical lattice system. So optical lattice is a potential for atom generated by the standing wave of light. So light is coming and reflecting by mirror. So and there is a standing wave appears. So and we can propose a predict potential like this one. So and then for in this kind of the setup, so at Hamilton is written as like this. So this is called as a Hubbard model setup. The first is says kinetic term. So this is a hopping from the one side to another side. And then yes. And the next one is the interaction term. So if the atom has two atoms in one side, so NLB it should be different for the from this one. So this or this terms. Otherwise, the potential terms. So this is I would say so trapping potential means some difference. So, but it is important one is this kind of parameters appear here, but it is very easily to choose this parameter in the case of optical lattice systems. And also, and in this means that this Hamiltonian is already same as the electron is optical solid electron is a solid state. So and this means the optical fermion optical the cold fermion is optical lattice can be simulated as electron is a solid state system. Okay. So if if we consider the advantage of the cold atom as a quantum simulator, so probably so there's a many let's say so advantage I already. First is this has a very large microscopic quantum system. So in that case, the atom number is relatively high, 10 to 5th. So, and also this is very clean, so no impurity and no lattice effects. And also this high controllability of have possible. So, and also we can change the boson, fermionic isotope, and geometry can be changed and dimensional change. And also this is a quantum isolated quantum system. And in addition, so we can use a various detection method. Or user one is measuring the momentum distribution, and of course it is possible to recently, so it is possible to directly the positions out of the traps is possible by quantum arithmetic techniques. And also we can measure the Cauchy momentum can be obtained. So and also we can make the spectroscopy as well. Yes. So now by using of this BC and the atoms, so we already demonstrated many kind of experiments. But today, so I will talk about the non-equilibrium dynamics and this and the non-equilibrium system and the SUN system. So this talks. Okay, so now I move to the boson model and the non-equilibrium dynamics after the query. And also, and if you have a question, so please write down your question to the chat. So probably I can answer that immediately your question because I check the chat all the time. Okay, so so always so I explain, but okay, so so both atoms in the optical lattice has a very good advantage as a reason. So many experiment with non-equilibrium using both atoms is performs. So for example, the light cone light propagation of the correlation, and also thermalization through the entanglement and the build up of the long range coherence can be already demonstrated. Of course, and the many another experiment is now reported. So and here I today so I talk about the boson fermion. So and now in that case we talk about the boson cases. So now my was so interesting this. So it's possible to measure another kind of interesting parameter directly. So now I ignore these potential terms here. So and it is is it possible to measure the ensemble average of the kinetic and the interesting term directly? So my answer is yes. So and in our case is especially this is possible because we use 2 electron atoms such as intermediate cases. And so to my best knowledge, so no experimental measurement in isolated many body quantum systems or another system is reported. So I'm very, I believe this is very important works. So I quickly explain how to measure this ensemble average of the kinetic energy and interaction. First is the kinetic term. So the kinetic term, so we obtain the time of image, time of flight images as shown in this slide. So the atomic distribution after the time of flight is obtained as shown in this kind of equation using the one function. So we can we know the difference. So roughly between the express another, let's say, so approximate term. So, but anyways, we can write calculate this kinetic term as like this one. So from this image, so we can obtain this kind. K is this sum, this one. And then so this is the interaction term can be obtained from the occupancy resolved spectroscopy. So actually, so we can using a singlet cell to root P2 states. So actually, so we can obtain this kind of spectrum. So this peaks correspond to the single occupancy atoms, and these peaks correspond to the double occupancy site, and this corresponds to the triple occupancy. So by using of the this spectrum, so and also from this area of spectrum, so we can obtain the this this ensemble average of this interaction term can be obtained like this kind of formulas. So now I talk about the quench system case. First, we prepare the isolated mode states. This means 1 atom per 1 per size. So we suddenly decrease particular lattice steps. So the atom is started hopping. So after some whole time, so we perform the measurement of the internal interaction energy and the kinetic energy individually. So this here is our expected results of the one-dimensional cases. So then blue data shows the interaction energies, and the red curve shows red data shows kinetic energy. So and then green curve is the total. Total means the sum of this sum of the kinetic and interaction energy. So first we observe the very rapid growth of the kinetics interaction energy, but total energy is almost constant. This shows that the conservation of the total energy during this quench, because this t equals 0 is this position, and there is no potentially changing. Also, this system is an isolated system. So the total energy must be the constant. And also this solid line shows a numerical calculation using this experiment. In there is a max product state, the method using the max product states. And then so this shows a very good consistency without any fitting parameters. So in the case of the 3D cases, so almost same experiment can be done. So the similar dynamics after quench appears shown in the 1D cases. And also this solid line means another other numerical result using another the numerical calculation method. But anyway, this is this shows solid line shows a good consistency without any fitting parameters. But from this quench experiment, so you can obtain another parameter, so non-local correlations. So this is, for example, delta equals 3 cases. So this is a correlation between this one, this, and this, and this, and the sum of all this, so parameters. So so in that case, so this is a result, experimental result of this one. So this is a distance of this delta, and then this is a time of holding time difference. So you can see that correlation is first appear, but then this is propagated to ballistically. And also, and for that, this is a theoretical result. So this is very consistent with the experimental numerical results. Okay, so now we check this experimental theory by the quantitatively. So we can show the very good consistent without any parameters. So and one the case is the experimental theory is almost very good consistency. But similar experiment can be done in the 2D systems cases. As for the 2D cases, we can measure the similar experiment. But in that case, non-local correlation is also appear. So, but unfortunately, so in that case is so numerical result is written in the solid state, and the expressed data is shown at this point. But in that case, we can show that so consistency is not so good. So qualitatively, this is consistent. But I think that further improvement is necessary for these 2D cases. So anyways, we can show that good consistency with up-to-date numerical calculation without any fitting parameter for the non-equivalent systems. And also, so we can show that, let's say, so in that cases. So probably so in that cases, we can check the good consistency, the 1D cases. So and we can we can check the 3D or 2D cases. So for the energy conservation, your energy distribution is a very good consistency. But for the non-local correlation, so probably so consistency not so good. So and further improvement might be necessary. So I would like to move to next topics. Is okay. So now I move to the next topic.
Professor Takasu,
yeah.
would you like to take questions now from the audience? So maybe I have missed some parts. So when you say atom correlation, how do you define what kind of correlations are you measuring?
This means that so-called this kind of correlation. So one body correlation or one body grid function, right? This kind of.
Okay.
It's okay.
So there is. Okay, you can continue now.
Yeah, thank you very much. Okay. So now I move to the second topic. So Fermi-Hubbard model, so short range SUM magnitudes. So now, of course, and I now talk about the Fermi cases. So in the case of the Fermi atom, so the previous experiment is already widely aggressively demonstrated. So in that case, is currently the Motto insulator is already measured. And also the spin correlation or long range magnitude is also measured by the Hubbard group. So by using the quantum gas microscopy, so very good checkerboard pattern appears. So and for much lower temperature, so many people believe that the D wave superfluidity must appear, but unfortunately, so I believe that this is not expected yet because of temperature problems. Okay, so actually, so this experiment almost experiment is using the lithium or the potassium. So two component effectively to complete fermions using different experiments. And then first, so this experiment is using the ATH Professor Chima Slinger groups, and also using the short range quantum magnitudes as measures using the portage, and then also for the rice groups, Hewlett groups, so it measures the 3D lattice using the reaching. And recently, the experiment is moved to the experiment using the quantum gas microscope. So, and the very many experiments performed. Yes. So, but so now we consider that we focus on the Fermi atom. So, and I'd like to use create a Fermi-Hubbard model with SN spin symmetry. And also for the interface, I use this isotope. So this isotope Fermi also has 6 spin freedoms. So we can important one is in that case is so the interaction. This interaction and the hopping is independent to this nuclear skin MIMJ. So this is very important. So important for the SUN physics. And in addition, so in that case is we can prepare the SU4 and SU2 system by using the optical pumping method. So this is a spin selective imaging by using optical cellular imaging. So first we measure the 6 components, but after optical pumping, so 2 or 4 was the atom only the spin component can be. This is also a good advantage. In the viewpoint of the theoretical study of SUN Fermi-Hubbard model, so many things are in place. So for example, we consider the half-filling cases, 1 atom per atom per site case. So in that case, the SU2 case is very well known. The ground state is shows the anti-ferromagnetic. So this shows a checkerboard pattern. But for example, the SU3, 4, or 5 cases, so ground state is not so clear. So it may be the long range spin order, but it may be the spin like liquid-like state. So but anyway, it is not clear. So this is a very this is a big motivation for the experimental research. So in addition, so we must consider the problematic cooling effect. So for the technical reason, the initial atom is not non-zero. So actually, so in our experimental setup, so lowest temperature is 0.1 times the temperature. So, but in optical, yes, and sorry, and this is initial entropy per 1 is also 1 times the Boltzmann constant. So, and if we load this atom to the optical lattice system, so if the spin is completely randomly, so in that case, completely randomly, so one atom has entropies of this kind. This is so this means that this is the minimum entropy with if the atom is a non-correlated system. So this is very fortunately, so our initial entropy is more than the SU2 case, but SU4 or SU6 case is less than the SU4 and SU6 case. So this means that so probably so if we load the atom to the SU4 and SU case, so higher threshold entropy, so for onset of spin entropy, so than our initial entropy. So and very it is possible to study the quantum magnetic of SN system in our setups. So now I quickly explain how to measure the nearest neighbor spin correlations. First, I load the atoms. And then we freeze the spin freedom, so by using the optical lattice. And then we apply the potential gradient. And then in that case, it's a singlet vibration oscillation occurs. So in this case, so wave function is this one. Right? So yes. So in that case, we use our so resonances. So first, this are motivated by the children Slingers groups, and they use so magnetic field. But for our cases, the atom is insensitive to the magnetic field, so we use the optical fields. And then we merge the atoms to one side. So this singlet atom, in that case, two ground state connected to the two ground atoms. But in the case is this state connected to one atom is in the ground state. The one atom is a vibration high state. And then we shine a hot association that this atom should be removed. So we can measure the singlet triplet atoms by atom process cases. So this is the experimental result in the case of SU4 fermion is just dimerized. Dimerized means this kind of setups. So this graph shows us atom number, remained atom number after the singlet tripletion occupation times. And this is well fit by this kind. This was so functions. So and then we individually measure the initial atom numbers. So we can measure the so atom loss. So this must be the singlet initial singlet atom number NS, and this must be the singlet triplet number NTs. So and then we define this value normalized still amplitude like this. A is this difference. So so sorry, small a is this one difference. So and then we can this is connected to so the spin this parameter. So and then we can compare to this result with the theoretical one. So in that case, we can estimate the temperature 0.4 times TD. TD is this hopping. And this is a SU4 system. So, but it is difficult to the same experiment to the SU6 system because we create a potential gradient by optical light shift. But for the SU6, but this value is different for the different spin components. So in that case, there's a 3 STO frequency must be here. So, but unfortunately, so after some improvement of the atom stability, atom number stability of setup, so we can measure this oscillation very clearly. So this is our experimental results, and this is a theoretical as a function. So this is very consistent. Of course, and this is so connected axis is very strong versus oscillation, but for the independent direction, so there is no oscillation in this one. So and this means that no spin correlation around this. So and here is our experimental results of the measurement of spin correlation. So this graph is this is a singlet traverse imbalance. So as a function of the initial atom entropies. So this green shows a singlet, SU6 singlet case, and this red shows a SU6 3D case, and this blue shows us SU2 1D cases. So so and easily you can see that so spin correlation was enhanced in the case with high speed freedom compared to the blue and the green results. So and this solid line shows a numerical result for 1D cases. So both green and the blue for blue cases. So exact dimensionalization and the local tensor operation is used. For the 3D cases, non-determinant quantum Monte Carlo method is used. But unfortunately, so this is probably so the calculation during this is invalid. So only limited this. Limited to this one. So and we can estimate the temperature in the optical lattice theoretically. So we can this graph shows temperature estimation. So this is still in balance, and also this is temperature. So in that case, is we know the experimental assay. So this one. So this is FSS with a finite size scaling. So probably so we can measure estimate temperature this one. Of course, it is possible to do by the entropies. Also this one, and also result is this one. So this is from the spin correlation measurement, such as entropy measurement. So and the result is this one. So two errors. So this is come from the theory of course almost and also experimental errors come from this one. So and this is so I believe that this is the lowest temperature of the Fermi-Hubbard model. So increase the SU2 step using ultracold. So very low temperature can be obtained. So yes, actually at this point, so this one. So and so this means that we believe that SU and U fermion system. So for example, our 173 white television with SU6 symmetry, so joins the quantum multiverse. Okay, so now I conclude my talks. So and I talked about the two topics. So this is the dynamics of the sudden quenchable systems and observation quantum magnetic ratio steps. So probably so in that case, in the viewpoint of quantum simulation, so we use a very consistency in the 1D case for both the quench and the spin correlation system. But unfortunately, so probably for the higher dimension, for the but an improvement might be necessary for this one. So for the boson case, energy is consistent, but the non-local correlation is not so good. And for fermion case, is probably so no. Anyway, the calculation this no valid calculation might there is no good. So yes. Anyway, this is the final summary. So some progress is shown here. Okay, so probably so yes. And of course, it might be. This setup can be used, so the Fermi-Hubbard model, and also probably so we can measure any measurement via spin correlation measurements. For example, the Heisenberg model or TJ model might be possible. So, and also for this case is we are interested in the non-standard lattice. Because we already create a leap lattice or bracket lattice, and also now we are considering how to measure the spin correlation measurement or long distance, so like quantum gas microscope method, because in that system it is very difficult to install this technique. So, and also now we are interested in the control doping, so it's also more interesting systems. That's all. Thank you for your attention.
Thank you very much, Professor Takasu, for the excellent talk.
Yep.
Now we have a few minutes. You have finished before time. So questions or comments from the participants? You're welcome. I don't see any question in the chat box. So I have a question.
Yeah.
You described how to measure spin singlet triplet oscillations using a light field with intensity gradient. I could not follow exactly how intensity gradient helps you to detect the oscillations.
Yeah, just a moment. So probably so. Just a moment. Yes. So in this case, is of course, yes, this was a gradient can be inserted. So this is so done by the. So first we prepare the atom as like this one atoms. So sorry, and then we shine our light as this kind. This is a light. So and we so we display it. So and then we so gradient is generated. And this is a usual Gaussian case. Is a profile is like this. But and of course we can we can calibrate the this gradient. So in that case is we use this spin this is also the same position. So in that case is atom is initially here, and then the gradient there is also so right is here. So in that case is atoms feel the force as like this. So and then in the TIFR case is so actually so atoms is moving to this one because we so and in that case is we measure this displacement, so we can calibrate and check the gradient, actual gradient parameters. This one. Is that answer your question?
Yes, yes. Yes.
Yeah.
Now it's clear. It's clear now. Thank you very much.
Thank you.
Anyone wants to ask any question? So if there is no more question, let us thank the speaker for bringing new dimension to the physics, SUN physics and SUN magnetism. So it's a new area. So hopefully the students will be encouraged to take up the new challenges in this area. So thank you very much. Now we move to the next topic, next talk, and our speaker is Dr. Misra. Dr. Misra is an assistant. Dr. Misra, can you hear me?
Yes, yes, I can hear you. Hi, hello.
So in the meantime, you can prepare your slides, and I can introduce you to the audience. So he is an assistant professor at the Department of Physics, Indian Institute of Technology, Guwahati. For the international audience, Guwahati is in the northeast part of India, in the state of Assam. Dr. Misra received his PhD from Indian Institute of Astrophysics in 2009. He joined Indian Institute of Technology Guwahati in December 2015. His research interests include theoretical aspects of quantum phase transitions in strongly correlated systems, ultra-cold atoms and molecules, topological phase transitions, and circuit quantum electrodynamics. Today, he will talk about entrant localization in a one-dimensional quasi-periodic double-well lattice. So with this brief introduction, may I invite Dr. Misra to present your talk. Thank you.
Yeah, thank you very much, Professor Dev, for this kind introduction. And it's a very good afternoon to all of you. And I would like to thank all the organizers to have this meeting. It is a very good meeting, and also giving me this opportunity to discuss our recent work here in this platform. So this is the last talk, so I may try to use the open boundary condition if necessary, but maybe not. I may finish it within time. So I'll be talking about this physics of re-entrant localization transition in a quasi-periodic double-well lattice. So we are from IIT Guwahati. So Guwahati, this is one of the most beautiful picture in of IIT Guwahati. And there are several such pictures. This is a very beautiful campus. I would suggest people to visit once this pandemic gets over. And yeah, so today's talk will be on re-entrant localization transition. And for more details about the work, one can actually visit this reference, this recent article. And some of these things I may talk today, which are ongoing right now, some of these results. So let's see whether I can reach there. So this is the brief outline of the talk. So I'll first talk about this single particle localization, which is known as Anderson's localization. And then I'll talk about localization in quasi-periodic lattice. Then I'll briefly introduce the double-well lattice Then we'll study the localization in double well lattice. Then finally, we'll see how reentrant localization happens. And if time permits, then I will talk about possible experimental signature of this physics. Okay, so first I would like to discuss about this Anderson localization. So since I have a very big title, I will hide some parts of the title and open up slightly to show the relevant physics in respective slides. So here I'll be talking about localization transition in a lattice. And the most famous paper related to this is the first paper by Anderson in 1958, which talks about this absence of diffusion in certain random lattices. So what this paper says that if electrons experience some random potential in a lattice, then there is the diffusion stops to occur and the transport is ceased. So that means the electron wave function can get scattered multiple times with this random potential, and then finally this electronic wave function exponentially decays within certain localization length or localization volume. So this analysis was based on this simple Hamiltonian, which has two different terms. So the first one is the random potential, and second one is the hopping between the nearest neighbor sites. These are electronic creation and annihilation operators. This is a simple problem, and of course this is in one single particle physics. So what Anderson predicted was that for a sufficiently large ratio of W by J, all the single particle states in the system are localized. Okay, so this is known as Anderson localization, and this was one of the most important findings in the last century. So it says that exponential, due to this localization, there happens some exponential decay of the wave function, and this leads to this metal to insulator transition. That means electron wave function goes from delocalized nature to localized nature. So that means your conduction diffusion stops. So that means you get some metal to insulator transition. So in this cartoon picture, you can see that this is an extended wave function. It is a normal periodic lattice where electrons can hop around between the lattice sites. But the moment you introduce some kind of disorder in the system, you can see that this electronic wave function gets exponentially localized. And this is one of the very interesting manifestation of quantum mechanics. Even though electrons have finite kinetic energy, they can actually stop by this. They can stop by this random potentials. Okay, so this was happened. This happened in 1958. But in the next 20 years, many things happened. But the most remarkable was in the year 1979, when this famous gang of four, where Anderson is one of them, they proposed a theory called scaling theory of localization. And in this theory, they discussed about how localization transition depends on dimension. And about this, yesterday Robin Kaiser actually discussed a lot about this picture. This is one of the most famous picture in the context of localization transition. So the key finding of this analysis is that in 1D and 2D, there exists no metal to insulator transition. So this means for any finite value of disorder potential, the system goes from, the system immediately becomes insulator. Okay. However, in 3D, there exists a transition, there exists a critical value where there occurs a metal to insulator transition. So looking at this graph here, one can understand how this thing happens. So apart from the serious analytical work behind this physics, behind this prediction, one can easily understand that for, if you define this dimensionless conductance G, which is G over E squared by H cross. So what this gang of four did was they defined this beta function, and looking at this conductance, value of conductance at different extreme regimes. For example, in metallic regime, this is the ohmic behavior of conductance, which goes as L to the power D minus 2. D is the dimension of the system. And in the insulating phase, this conductance decreases exponentially. So these are the two extreme cases in the metallic phase and in insulating phase. But if you look at this beta function, then you will see that for insulator, beta goes as log of G, for metal, beta goes as D minus 2. So, and this intermediate things have been extrapolated. So if you look at here, in this part, for dimension 2 and 1, this beta is always negative. So that means this conductance always decreases as you go on increasing the length of the system. So this arrow indicates the length of the system. In both 1 and 2D, the conductance decreases. However, in 3D, there is a transition in where this beta goes from positive to negative value. So that means there is a transition at some critical point. So this gives this metal insulator transition in 3D. However, there are no transitions in 1D and 2D. Okay, so this was very important. I mean, very important finding which says that there is no transition, no metal to insulator transition in dimensions less than 3D. In the subsequent year, just in 1 year after, Aubry and Andre, they proposed that true disorder is not necessary to see single particle localization in one dimension. So what they propose is that you don't need true disorder in the system. The single particle localization can actually happen in presence of quasi-periodicity in the lattice. So quasi-periodicity meaning it is neither properly perfectly periodic nor disorder. So you can have incommensurate lattices. For example, this Hamiltonian which says that which has two different terms again. This is the hopping matrix element between two different neighboring sites. And this is the extra term which is different, slightly different, not slightly different. This term is different from this Anderson's model, where this term has a strength, delta, and this cosine term, which gives rise to this quasi-periodicity in the system. And the quasi-periodicity can be introduced by choosing a suitable beta, and beta is in general an irrational number. And one has to choose beta in such a way that it is the ratio between two adjacent Fibonacci number. When the Fibonacci numbers are very large, then this gives you the perfect quasi-periodicity in the system. So Aubry and Andre suggested that if you have a quasi-periodic system like this, model like this, then one can actually see transition, single particle localization transition in 1D, which is completely different from Anderson's prediction. So this is one of the very important finding of Aubry and Andre. So this model has a peculiar property of self-duality. Self-duality meaning if you make the transformation of this model to momentum space, then this model is equivalent in the momentum space. So the real space and momentum space transformations are equivalent at this point when delta by j equal to 2. So that means the states which are localized in the real space are extended in the momentum space and vice versa. So that means there exists a phase transition at this critical point delta by j equal to 2. So if you look at in this cartoon picture, so if I increase this delta by j, which I call disorder strength in this case, although it is a quasi-periodic strength, so you can see that all states localized to, extended to all state localized at this delta by j equal to 2. Okay, so this is the key finding of this Aubry-Andre model. Now this can be easily seen from the energy spectrum. To see this physics from the energy spectrum, one can use these diagnostics known as this participation ratios. The first one is called inverse participation ratio, which actually indicates the localization property of this system that can give rise the extent of localization. So if the single particle states are localized, then this quantity is finite and large. And if it is extended, then this quantity is 0. And the other quantity, which is called normalized participation ratio, by definition, this is actually 0 in the localized state and it is finite in the extended state. So looking at these conditions, one can distinguish between localized and extended states. So if you plot the energy spectrum along with their IPR values, so this color bar is for IPR strengths. So you can see that this part is completely dark before delta by j equal to 2. This means these are extended states and these are localized states. So similar physics can be seen from here if you plot the eigenstate indices with respect to their IPR value. So this dark patch is, this corresponds to the extended state, and the right side colorful patch is for the localized state. Now if you take average of all these IPRs over all these states and plot them together, you can see that there is this nice sharp transition point from where this IPR becomes finite and NPR becomes 0. So this is exactly happening at delta by j equal to 2. So this is a critical point where this metal to insulator transition is happening, or all states extended to all state localized is happening. Okay. So this finding of Anderson localization in one dimension was first observed in these experiments of Alain Aspect and Massimo Inguscio. In these two experiments, where Alain Aspect used this speckle pattern to observe this localization transition. Here you can see at t equal to 0, the Bose-Einstein condensation cloud is in the trap when they release. When in the presence of a disorder, you can see that there is an exponential fall of this atomic density, which can be seen from here. The central peak is the initial position, initial atomic density. After a certain time, you can see this exponential tails indicating the localization transition. On the other hand, Massimo Inguscio's group, they constructed this bichromatic lattice, which is a quasi-periodic potential, by superimposing a deep periodic lattice with a shallow periodic lattice with a different period, which is incommensurate to the previous lattice. If you combine these two, then you get this quasi-periodic lattice. Okay. So if you load BEC to this quasi-periodic lattice, a cloud of Bose-Einstein condensation, they are non-interacting particles, so you can treat them as single particle physics. So if you load them and you release the trap, then you see that this cloud is expanding in absence of disorder. It's a free expansion. But if you increase the strength of disorder, then you see that cloud is not expanding. So that means you are in the regime of Anderson localization in 1D. Okay, so these are the very fundamental observation of Anderson localization in 1D. Now, another interesting concept regarding this Anderson localization in 1D is that if you break the self-duality of this Aubrey-Andre model, then you get the concept of mobility edge. And this mobility edge is nothing but the critical energy separating the localized and the extended states. So if you break the self-duality, what will happen? Instead of all states going from extended to all state localized, what you get is that there will be a critical regime where both extended and localized states will survive. So this means in this cartoon picture, if you look at here, this is the disorder strength increasing from here. Instead of going directly from all state extended to all state localized, there will be a critical regime where both extended and localized states will survive. And the critical energy separating these two regions in an energy spectrum is known as the mobility edge. And there has been a lot of debate how to obtain this mobility edge, what kind of model one has to introduce, and so on. So there are a series of papers proposing the existence of this mobility edge and critical region. And there are, of course, special cases known as the generalized Aubrey-Andre model, where this self-duality still exists, but one can actually introduce this mobility edge. For this interesting finding, one can read this review article by a group of Subrata Mukherjee and others. However, recently in 2017, Das Sharma and group, they predicted that this mobility edge can still be found in a bichromatic lattice if you stay away from the tight binding Aubrey-Andre limit. So Aubrey-Andre model is a tight binding model where this atomic, the lattice sides are very, very deep. So what they propose is that if you keep your lattice depths very shallow and you are in the 1D bichromatic regime, then you can still find the existence of mobility edge or critical regime. So so what they have proposed in this model is that there is a continuum Hamiltonian because it's not tight binding. So they have two different lattices. They can create this incommensurate potential. This is the primary lattice. This is the disorder lattice. So with this Hamiltonian, what they have obtained is that you can see that this dark patch is not directly going to this red patch at a particular value of BD. But what is happening here is that there is a patch here. You can see that if you go on increasing, if you go along the y-axis, you go through this localized state and to the extended state. So that means for this value of disorders, you have both extended and localized states. So this is the critical regime, and this line indicates the single particle mobility edge. So if you plot the IPR and NPR, average IPR and NPR for this case, you can see that there is a region here where both IPR and NPRs are finite. So that means the system is going from extended to all state localized via this region called critical region where both these IPR and NPRs are finite. Okay, so immediately after this proposal in the next year, in 2018, Emmanuel Bloch's group, they actually studied this model in their cold atom experiment, and they observed this phenomena. They observed the presence of this critical phase in the experiment. What they studied, what they tracked down is this density imbalance in their experiment and also edge density fraction. So if the states are localized, So what they observed is that this is a density imbalance between even and odd sides of the system. If the system is localized, then this quantity will remain finite in the long time evolution. And if the states are extended, then if you create a particle in the left side of the lattice, that will definitely propagate to the right side of the lattice. So this quantity will remain finite in the further extended states in the long time evolution. So these are the theoretical predictions. So you can see that in the extended regime, D is finite and it vanishes in the localized regime where this I is becoming finite. But you have a nice intermediate regime where both these quantities are finite. And this is the experimental prediction on the right. So this is the critical region. And this is one of the very interesting and I think first observation of mobility edge or the critical region in cold gas experiment, in one dimension using cold gas experiment. Okay, so what is the summary so far? So what we have learned up to this point, we have learned that in one dimension there is no localization transition with true random disorder. However, if you introduce quasi-periodic disorder in 1D, that exhibits localization transition. For example, the Aubrey-Andre model, the transition from all states extended to all state localized due to the self-duality condition, and the breaking of self-duality leads to the critical region where both extended and localized states are allowed, and that also gives rise to the existence of mobility edge. After the localization transition, all states remains localized no matter how strong the disorder strength is, and that is quite usual because if you increase the disorder strength, the states will remain localized forever. What you can see from here, once the states are localized like this, if you go on increasing this axis, VD along this axis, they will remain more and more localized. This thing will become more red and red, like yellow and so on. Okay, so is this last statement unique? Can you ask a question whether this statement is always true? So to see this, what we have done, we have considered a double well lattice. So now, what is a double well lattice? Double well lattice is a series of double wells where the particles experience two different hopping amplitudes. For example, T1 and T2, one is large, one is small. And when T1 is, at some point T1 is larger than T2, at some point you can make T1 smaller than T2. So this is called dimerized lattice, and depending on this dimerization, you may have different interesting phases in this system. So it was first discussed in the context of polyacetylene, and the model which describes this system is known as this very famous Schrieffer-Higger model, or the SSH model, which is given by this. And this has two different sublattices, A and B, and these are fermionic creation and annihilation operators. So if you look at the energy structure spectrum of this, so you can see that the dispersion gives rise to interesting physics here. When T1 is greater than T2, you have a gapped dispersion, and when T1 is less than T2, you have another gapped dispersion. But if you go from T1 greater than T2 to T1 less than T2, at some point there is a gap closing region. Okay, so you go from a gapped region to another gapped region through a gap closing point. Okay, so this interesting feature of this model gives rise to the topological property or topological phase transitions in this kind of SSH model. Okay, so this was this model preserves chiral symmetry. If you look at the band structure here, the band diagram, you can see that this delta is T2 over T1, that is a dimerization. This is the order control parameter here. If you look at this energies, you can see that this is a gap phase on this side when delta is less than 1. And on the other side, when delta is greater than 1, we have another gap phase, gap region. But only difference between this state, this region, and this region is that this region hosts two zero energy edge modes. Okay, so this is the difference between this and this. So this is known as the topological region. This is known as the trivial region. And this topological region possesses this edge states, which can be seen from this amplitudes at different sites. You can see these edge states are the amplitude at the edges are finite. However, if you go to this bulk somewhere here, you see that the particle remains in the bulk. Okay, so this is the topological property of this double well lattices. And what we are up to here is that we are going to study the effect of quasi-periodicity in this kind of SSH model or in this kind of double well potential. So here we introduce the quasi-periodic potential in this along with this lattice, And you can see that this is nothing but Aubrey-Andre type potential, where we have separated the sublattice potentials like lambda A and lambda B. So in the limit T1 equal to T2 and lambda A equal to lambda B, we get back to our usual Aubrey-Andre model. So for T1 not equal to T2, the self-duality is broken. So that means this is no more same as real and momentum space. So what is the effect of disorder in such systems? Okay, so control parameter is delta, which is T2 over T1. When delta is less than 1, we have trivial phase. When delta greater than 1, we have topological phase. Now we explore the effect of lambda in both trivial and topological regimes by tuning delta. So we choose beta as this golden ratio and choose lambda A equal to lambda B equal to lambda. We call it as the uniform case when both these strengths are same. And we consider fairly large systems like 13,530 sites. And then we look for different diagnostics in the system. So these are the famous diagnostics we discussed, which is inverse participation ratio and normalized participation ratios. For delta less than 1, we have a gray patch over here where both NPR and IPRs are finite. And for delta greater than 1, we of course found some critical region where both NPR and IPRs are finite. So there is nothing surprising here because this is a self-duality broken system. So you get a critical region where both IPRs and NPRs are finite. Similarly, on the topological side also, we are getting the same critical region. So only difference in these two cases is that in the energy spectrum, where you can see that there is zero energy 8 states which appear in this case. There is nothing, no zero energy states on the trivial side. And eventually these zero energy states will become energetic and they merge into the hybridize into the bulk energies. Okay, so now this is not so surprising as I mentioned. Now we go to another case. So what interesting can be drawn from this kind of model? So what we have done, we just change this lambda A equal to minus of lambda B, that is equal to lambda. So what we have done is that in every alternate site, we change the strength of this sign of these lambdas. For example, in the first site, if it is lambda, second site minus lambda, third site lambda, minus lambda. So it's kind of staggered disorder case. So if we introduce this kind of quasi-periodicity in the lattice, then what happens in the system? So now I discussed about this topological part. I'll show the trivial part later. So for the topological part, that means delta is greater than 1. So what we have obtained is this figure. So here the IPR and NPR are plotted. Once again, we see a critical region. So what is surprising here? There is nothing. So you get this critical region posting a mobility edge. So the system goes from extended to localized through this critical region. Okay. So now what happened for different deltas? So if we go to different delta, now something surprising is happening here. So for delta equal to 2.2 or so, what we have seen here is that we are seeing something strange. We are seeing two gray patches. That means two critical regions. Okay. So for delta, for a critical delta, we can see that as a function of lambda, we can see two different critical regions. So that means in these two critical regions, IPRs and NPRs are finite. So this is something different, which we did not see before. So this means what? This means this red line is IPR, which is 0 and it becomes finite. That means at this point, this is finite and NPR is 0. That means one phase transition occurred. Okay, extended to critical to localized. After that, after some critical disorder, we can see that this NPR becomes finite, bringing in another critical region, and eventually another localization transition is happening here. So this is actually the interesting feature of this. Why it is happening, why this NPR is becoming finite again after certain critical disorder strength. Because if you plot the individual NPRs for individual states, you can see that these NPRs are becoming 0 at some points here in some region, and then suddenly some of these NPRs are becoming finite. The NPRs of some of the states are becoming finite, and this gives rise to this small peak in this NPR, and that gives rise to the second critical region in the system. Okay, so this is indeed something interesting, and to verify that whether this peak, small peak over here, is really a peak, or it's a finite size effect. What we have done here is that we have performed this finite size extrapolation. And when we extrapolate this L to infinity, you can see that for different system sizes, as you go on increasing the length for L equal to infinity, you can see that the NPR is becoming 0 in this regime of disorder. And then it is becoming finite, and finally it is becoming 0. So this is a 1 over L plot of NPR. You can see that for 1.5 it is going to a finite value, then for 2 it is vanishing, then 2.5 it is finite, and then eventually it is vanishing. Okay, so this is the conformation of reentrant localization transition. So let me explain this to you with some further physical quantities. How can you see this in other quantities such as energies and eigenstates? You can see that this energy versus lambda superimposed with their IPR values. IPR, this is red meaning IPR equal to 0, blue meaning IPR equal to 1. So you can see that this straight line, this line here, tilted line here, that actually separates, that indicates the mobility edge. So up to this point, all states extended, and in this region there are extended as well as localized states, and in this regime only localized states, and somewhere here there is a red patch which is visible here where some states are becoming extended again. Okay, so this is the reentrant feature which can be clearly seen in this eigenstate index with this with their IPR values. So up to this point these are all extended, and this regime is extended plus localized, and from here to here this region is localized, and this red patch which is reappearing, that means some of the states are becoming extended. Okay, so we are going from extended to critical to localized, critical then localized. Okay, so the previous notion that when lambda becomes larger and larger, all these states remain localized after the first localization transition, it is no more correct. So we can enter into another critical region and localization can happen again, complete localization can happen again for larger disorder strengths. So we verified this for particular state, by plotting the IPR and NPR for a particular value of lambda across this point and across this region. So we can see that extended and localized states are separated here. So this indicates the critical region in this area. Okay. So we also see similar signature from density of states. Now, to summarize this physics, we obtained the phase diagram of both uniform disorder case and staggered disorder case. To obtain the phase diagram, we obtain this, we compute this quantity called eta, which is a log of IPR into NPR, which was actually proposed in this paper of Das Sharma. So you can see that in this phase diagram, this quantity eta is plotted along the z-axis. This color indicates the value of eta. So in the localized and extended states, this eta value is similar. They are all close to -4, and this blue region indicates the critical phase. Okay, so this delta equal to 1 line, this is the Aubrey-Andre limit. So you don't see any critical region. It's all red. It goes from extended to localized. But as you move away from this self-dual point, you can see this critical regime is appearing. So on the other side, in the in the trivial regime also you see a critical phase. In the topological regime, you see a critical phase, and the transition happens from extended to critical to localized. But if you go to staggered case, you see this interesting feature over here. There, after some critical delta, you see this reentrant feature. So the system goes from all state extended to critical, then all states localized, then to critical, then all state localized again. So this is a reentrant localization transition. So the system is system is getting localized twice. So it is getting localized first here at this point, and then entering a critical phase, then getting localized again. So this is happening in topological regime. And you can notice here that in the trivial regime, when delta is less than 1, there is no concept of edge states and all. Here also you still see this reentrant feature. So that means topology has no role to play in this kind of reentrant localization transition. Okay, so this is the delta equal to 1 line where there is this is the Aubrey-Andre limit. There is no critical regime. but on the both sides, you see this localization transition after some critical values update. Okay, so this was the finding. If I have, do we have some time here or?
Yes, you have 5 minutes.
Okay, 5 minutes. Okay, fine. Yeah. So after finding this reentrant feature in this model, so what we have done, we looked for some experimental signatures of this kind of physics, and we looked for the signatures in the quantum walk of this model. And quantum walk is one of the very interesting or useful tool to understand the physics of some system in a dynamical way, in the dynamical evolution of some initial state. This was actually discussed in great detail in the talk of Emmanuel Bloch, where they have used to predict many different interesting physics using this physics of quantum walk. So here what we do is that we create some initial state, and then we unitarily evolve it with respect to the system Hamiltonian like this. And using this time evolved state, we compute some observable expectation. And looking at this observable, one can see the behavior of, predict the behavior of this quantum mechanical state. So here what we have done, we have created a particle at the middle of the lattice, and then we time evolved it. And here we are plotting the density evolution in the quantum walk. So what you can see is that for lambda equal to 0, that means no disorder. There is a very, pre-particle evolution. This spreading is like, you can see a ballistic type expansion here. But as you go on increasing the value of a disorder strength, you can see this profile is getting decreased. It is slowly narrowing down. And then as you reach this lambda equal to 2 point, which is somewhere here. So I am going like this. I am going along this line, delta equal to 2.2. So I am going from extended to critical to localized. So you can see for lambda equal to 2, there's a very narrow profile here. That means it's a localized phase. And as you increase lambda, so you enter into this critical regime where this profile has to expand. So it's a slight expansion over here compared to this one for 2.5 and 2.8. And then for very large value of lambda, then you enter into this localized regime. Then again, you see this localized profile. And for large and large value, you get this localized profile. So this is kind of a reentrant phenomena. You go from extended to critical, then localized, then critical, and then localized. So this localization is happening twice. So this is why it is called reentrant phenomena. We also observe this root mean square displacement in this evolution. Root mean square displacement, which is computed like this. You can see that for lambda equal to 0, it's a ballistic expansion. As you increase lambda, you see this is slowing down. And you can see the reentrant feature here. For lambda equal to 0, 1, 2 is here, the green one. Then it increases for 2.8. Then again goes to 3. So it's like reentrant. Blue, orange, green, red, and purple. Okay. So this is again the reentrant physics here. So we also compute this edge density fraction, which was experimentally observed in the experiment of Emmanuel Bloch. So we can see that this edge density fraction for extended state is 1, then it is decreasing. Then for lambda equal to 2, for completely localized state, it is 0. For critical, it is becoming finite and then becoming 0. So it is again reentrant, finite, finite, 0, finite, 0. So reentrant feature is visible in this experimental quantity, which can be seen in optical lattice experiment. And then we look for the effect of topological edge state on this reentrant transition. So we plot this edge state behavior here in this graph. You can see this feature here. The energies are 0 for these two states for lambda equal to 0. And as you go on increasing lambda, these states actually go and hybridize into the bulk. And one of the state hybridizes first, and then the second one later. And this is the point where this gap closes. So if you look at the IPR of this state, which hybridizes first, you can see that there is a reentrant feature here also. The IPR is finite because the state is initially localized. This is a localized edge state. Finite to 0, then finite, 0, and finite. So this is another reentrant feature, but this reentrant feature is happening somewhere far actually, somewhere here, not close to where it is happening. So it is actually happening far from the band gap closing. So therefore, this has no contribution on the reentrant localization we are seeing here. This entire reentrant localization is happening due to the bulk state, not due to the edge state. So the edge has no role in this reentrant feature. Of course, they have their own reentrant properties. So here we plot the states, the amplitudes here for both these edge states. So here one is localized in the left end of the lattice, other is localized at the right edge. And then as you go on increasing lambda, one of the states gets hybridized to bulk. So it becomes delocalized. So you can see it is getting delocalized and then localized, then delocalized, then both of them gets localized. So somewhere here, localized, delocalized, localized, delocalized, localized. Okay. So this is the, again, reentrant feature of the edge states. And this is all I wanted to say. This is the summary. So what we have done is that we studied the localization transition in a quasi-periodic double lattice. While the presence of uniform quasi-periodic potential leads to one critical region, staggered quasi-periodic potential exhibits reentrant localization. For a range of hopping dimerization, the system goes from extended to critical to localized, then to critical, and then finally to localized phase. So edge state also exhibit reentrant phenomena, but they have no contribution for this bulk spectrum. So what can be done further? You can study the effect of interaction in the context of many-body localization. And can this many-body localization exhibit a second critical regime? And one can also study the topological properties in presence of this disorder, and so on. So my co-workers are Professor Sourav Basu, my colleague here in the department, and the PhD students Silpi, Ashirvad, and Suman, and Professor Bilal Tanatar from Bilkent University in Turkey. And thank you very much for your attention. These are a couple of beautiful pictures of our campus.
Thank you very much for a very interesting talk. And now this talk is open for questions or comments. Now there is one question from Kanaya Pandey. So Dr. Pandey, you can unmute and ask the question.
Yeah, so what I'm asking that about this super lattice you were talking about, that there are two lattices which are exactly, one is exactly in the center. So for example, you can make this kind of lattice using 1064 and 532 nanometer. But
yes, yes.
Many times, you know, it's, for example, we are not having 532 nanometer. We are having, for example, 800 nanometer. So what will be the situation in that circumstances?
No, in that case, you mean to get this lattice in your lab, you have to actually use one of the lattice. If one of the wavelength is lambda, the second one will have to be lambda by 2. Otherwise, yeah, you cannot get this exact double well structure.
Yeah, yeah. And but it is not exactly that. That's why I'm asking that what will be the situation in that circumstances?
Okay. So in that situation, yeah, so we are actually exploring that situation. If your lattice is not exactly like double well, so we are exploring that situation and we are getting some interesting features there in the reentrant, in the context of reentrant phase transition. So what we are getting is, I don't want to disclose it here, but briefly I can give you some hints. So we are getting multiple localization transition in this kind of lattices. So in principle, this kind of double well lattice, what I'm going to say is that this kind of double well lattice is not necessary to see this reentrant phase transition. One can actually have other lattices where this kind of reentrant transition can occur. And what you have rightly mentioned, that if you have a 1064 nanometer lattice and you have 800 nanometer lattice, we can certainly see some reentrant phase transition when your lab comes up. We'll definitely propose our theory to see some interesting reentrant localization transitions. That work actually going on is an ongoing work, so I don't want to highlight detail on that.
Okay.
Yeah. So basically, this physics is due to the competition between the disorder strength and the kinetic energy in the system. So if you can define some system where this disorder strength can dominate over the kinetic energy at some particular value like this, then this reentrant physics can appear.
Okay.
Yeah.
So if there is no more question, so let us thank the speaker for the excellent talk.
Yeah.
And I thank both the speakers of this session. And this program has come almost to an end. So before we formally declare this to be closed, let me express on behalf of the organizers our sincere gratitude to all the speakers, all the invited speakers who have delivered lectures here and given their time despite their busy schedule and many other commitments, particularly international speakers. And this program we will consider this to be successful if the participants are benefited by listening to the speakers and getting some intuition about the physics that ultra-cold atoms, molecules and ions can bring in. And so with this, I also thank all the participants for actively participating in this program, in this long 13 days program. We had school from 10th May to 19th May. We had 8-day school and 3-day this discussion meeting. So I then invite my co-organizers to say a few words. And also I can invite other speakers or participants to tell us about your experience about this school and the discussion meeting and about the quality and the way we organized the program. So with this, I invite Sourav, my co-organizer, to say a few words.
Actually, yeah, so I think it's a nice, it's been a nice meeting, and it's very nice that so many people participated in it. And I again particularly thank the speakers who have taken really care in tailoring the talk so that it is accessible to a really broad kind of audience, as we had talks in very different kind of fields, from Rydberg atoms to trapped ions, quantum computing to cold molecules, and so on. So it's been a really broad school, and I hope that at least for every participant, at least some of the talks have been useful. And actually, I would like to invite any comments or any suggestions or anything, anybody, including students, postdocs, faculty members, who would like to say anything about this particular school or the workshop or the discussion meeting, to please unmute their mic and share their opinion. But maybe before that, I should ask Saikat Ghosh to say if he has anything to add.
So I think, Sourav, you said everything. Yeah, just like few comments on the fact that as an experimental community in the country, we are kind of a very small and starting community. And this was one initiative greatly initiated by Sourav to get together, though unfortunately we couldn't get together physically. Hopefully there will be a follow-up meeting soon when things normalize, where we should be able to meet in person. And I sincerely hope that this will bring, this is one step towards bringing the community closer together. Yeah. Sadiq, I think.
Yeah, hi. I'd like to say a few things, actually. So first, I would like to congratulate you guys for hosting this meeting. It was a wonderful meeting. It is, I think it's unsurpassed in our country to have a meeting of this quality. Having been around in this entire area for a while, I mean, this quality of meeting is extremely difficult to organize anywhere in the world. And I do hope with the fact, because of the fact that the lectures are also online and they will remain current at least for a year or two before they get superseded by the new discoveries in these fast moving areas, that the students who have sort of been in some sense, I would expect that students are a bit let's say they have been exposed to some things very quickly, and I hope that the students who have participated take the time to revisit these lectures which are online, and so absorb a few things. One of the most important takeaways that I got, because I've been attending almost every lecture here, I mean barring a few things because of personal issues, but one of the things that I got out of this is it kind of hones you into certain directions, and it also tells us as a nascent Indian community of experimental guys and even theory where the big gaps are, and what actually, even more importantly than that, what is where the opportunities are. So this is extremely important, and I think this school and the discussion meeting has framed that very well, because finally is you have to fight the problem you can win it. So, and this kind of thing gives you an opportunity to assess what are those problems and define it for yourself. So thank you very much, guys. You have done a great job organizing this, and it is a very welcome thing in this dark
Thanks to
time.
Sourav.
Yeah,
Thank
yeah.
you,
I mean,
Sadiq.
everyone, Sourav included. I can imagine that he was, I mean, having known Sourav for a very long time, I mean, I can imagine that he put a lot of work in this, as he always does. So, but I mean, and thanks everyone. Yeah.
Thank you, Sadiq, for your comments, which are very encouraging. And I would like to invite Manos to say a few words. But before I invite, and I'm sure all of you agree that this meeting, online meeting, has been possible because of our audiovisual team. They did a fantastic job, because you can see for long 13 days, there was no disconnection and no technical glitch. And even after their working hours, usual working hours, they worked hard even at night, 9 o'clock, 10 o'clock. So we should give a big round of applause for their good work. Okay. Okay, and and also the ICTS ICTS program committee, we are very grateful to them for agreeing to our proposal and making it a success. So next, so I invite Manos from Singapore to say a few words.
Thanks, Bimalendu. Yeah, well, I think everything has been said. I just can't say more than that. First of all, let me say that it's excellent job by all of you guys. I mean, it's very, very difficult. I know the situation only from my personal contacts, and also I know from the family, things are very, very bad. Yeah. And under that situation, I could actually see that there were days like 5 minutes before things started, everyone was panicked whether this next thing would happen, that you can manage to be chairing this session or doing something or not. Yeah. This is very hard. Yeah. So just to say that you managed it, and not only managed it, but I think the school as well as the workshop has been excellent with the line of speakers that you had. It is, I mean, there is a good and a bad thing of this pandemic. The good thing, if we take it from there, is that we had this excellent list of speakers who could speak without being traveling to India. That's a good thing, is which we can take from here, and this is also good for the students, because particularly this has been said. I mean, this gives an opportunity to learn from the diverse work that is going on all over the world, and also kind of have their own ideas out of these. Yeah. So all of these can stimulate something new out of them. So again, going back to, of course, the ICTS school, I mean, we had done it before and physically. So but this time it is excellently managed. Yeah. I mean, not even, I haven't seen any glitch so far, whatever I was there involved in. Yeah. Congratulations. Yeah, I think everything will be put up online, and I guess you would have a physical meeting possible sometime soon. Looking forward to that.
Yes, yes, absolutely, yes. And any participant?
So I see one of the younger experimentalist members, Kanaya Pandey, is here. So he's one. So Kanaya, if you want to say something about doing atom trapping in India and how things are.
Yeah, I'm a bit, I mean, yeah, so it's there are a lot of progress happening. I mean, for when I joined as a PhD in India, I mean, a cold atom was a bit isolated and also kind of, a discouraged kind of field, in India, because, we were putting so much hard work to produce some result, while other field, I don't want to comment, but they are more fruitful somehow. So we had to keep ourselves, very strong morally to, sustain in this field. So, I mean, now it's the group is, expanding. It is very nice that it was organized and we could also interact with many people. So, I mean, it was an excellent program. I mean, I enjoyed immensely this program. Thank you very much.
Thank you, Kanaya, for your comments.
Professor Bhanudash, I can see also is here. Okay.
Yeah, okay, thank you. Well, there's not much that I can say. I mean, I can just, echo what everybody else has said. It's, I mean, extremely well organized, and, the choice of speakers, the choice of topics. I think it's so, congratulations to all the organizers, participants, and certainly the speakers, you see. I think one thing that I would like to say, I mean, this is more from the point of view of, quantum computing, but I guess, it applies to other areas as well. I think it's extremely important for groups to collaborate. And this is something that I've not been seeing in India. You see, that is, I mean, particularly, there are areas in, say, either trapped ions or cold atoms, where it's impossible to achieve anything substantial without collaboration. I mean, you can look at groups, for example, in the US, China, Europe, Japan, everywhere, that, something like, say, cold atom quantum computing or trapped ion quantum computing needs a lot of collaboration, And this is something which, people in the quantum technology mission have talked to me about, and I said, I mean, I can only talk to individuals, but the motivation has to come from the experimentalists. So this is something that you need to think over. And I hope, I mean, this particular, school and discussion meeting is a step in that direction. And not just between experimentalists, but also between experimentalists and theorists. Thank you.
Thank you very much, Professor Das. And Sister Sourav, can we now close it, or?
Yes, it's fine. If any student wants to say something, I would be really happy, actually. I don't want to call out anybody, but if not, then yes, we should just close.
So now this comes to an end. Thank you very much. Have a good weekend. And so now we can close it.
Thank you. Yeah,
Okay,
thank
stay
you,
safe.
everyone.
Take care.
Yeah, bye.
Bye-bye.